Imagine you are conducting a scientific experiment, meticulously gathering data and eagerly awaiting your conclusions. When your statistical analysis leads to failing to reject the null hypothesis, it signifies that there is insufficient statistical evidence in your observed data to conclude that the null hypothesis is false. Crucially, this does not mean you have proven the null hypothesis to be true. It simply means your data does not provide enough support to discard it. This concept is rooted in the fundamental framework of hypothesis testing, which operates on a principle similar to a legal trial. The null hypothesis, often denoted as H subscript 0, represents a statement of no effect, no difference, or no relationship, much like assuming a defendant is innocent until proven guilty. The alternative hypothesis, H subscript 1, is what you are trying to find evidence for, suggesting an effect or difference exists. We collect data and use statistical tests to see if our observations are so extreme that they would be highly unlikely if the null hypothesis were true. If the evidence, often summarized by a p-value, does not fall below a predetermined significance level, typically 0.05, we cannot reject the null. This threshold is our criterion for deeming an observation statistically significant. Failing to reject the null hypothesis implies that your observed effect could reasonably be due to random chance, given the assumption that the null hypothesis is correct. It underscores that our tests are designed to find evidence against the null, not to prove its validity. Think of it as reaching a verdict of not guilty due to a lack of incriminating evidence, rather than an affirmative declaration of innocence. Understanding this distinction is vital because incorrectly interpreting a failure to reject as proof of the null can lead to erroneous conclusions and stalled scientific inquiry. It highlights the potential for a type 2 error, where a false null hypothesis is mistakenly not rejected, meaning you missed an actual effect that was present. When you encounter this outcome, consider the practical implications. It might indicate that the effect you are looking for is very small, your sample size was too limited to detect it, or there was too much variability in your measurements. It is a signal to carefully reevaluate your experimental design, refine your hypotheses, or explore different data collection methods. This outcome is not a dead end, but rather an invitation for further investigation. It encourages researchers to delve deeper into potential confounding factors, explore larger datasets, or employ more sensitive analytical techniques to uncover effects that might initially be obscured. Embracing this nuance improves the rigor and integrity of scientific research in fields like machine learning and artificial intelligence, ensuring that conclusions are drawn with appropriate caution and precision.